Hello, how's the sound? Oh, we'll lose this. How's the sound now? Better? Okay, thank you for the thumbs up. Okay, my name is Witt. I am currently a postdoctoral fellow at Northwestern University and the Adler Planetarium in Chicago. And I'm also the co-chair of the detection working group within the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav. So as a member of NanoGrav, I'm also a member of the International Pulsar Timing Array. So all the results I'm going to give you today are on behalf of a very large community like your own that is unified by this broader goal of detecting these low-frequency gravitational waves. So as we've shown a few times today in a few different versions of this figure, there's quite a few different regimes of gravitational waves that are out there in the universe. So far, as we know, we've only been able to detect high-frequency gravitational waves from smaller gravitational wave sources like black hole binary inspirals, merging neutron stars, compact binaries. As you all well know, there is this medium regime of medium frequencies, medium masses that can be detected by gravitational wave detectors in space, like LISA. However, down at the lower end of the spectrum, lower frequencies, we also have the most massive types of gravitational wave sources, supermassive black hole binaries, as well as the stochastic background made up of all of the gravitational wave sources within that low frequency band. And because these are all very different sources, we need different types of detectors to actually be able to seek them out. We've heard lots about ground-based detectors as well as space-based detectors here at this conference, but today I wanted to give you all a little bit of an update on galaxy-sized detectors called pulsar timing arrays. The general idea here is that rather than constructing a laser-based gravitational wave source or a gravitational wave detector, instead we are using these naturally occurring objects called pulsars. These are neutron stars that are remnants of a very massive star that happen to be beaming out radio emission out into the universe. So rather than using a very large, heavy mirror at the end of a laser cavity as our test mass to detect our gravitational waves, we use the pulsars themselves that are emitting their own radiation, so as the gravitational wave passes, we can actually see how the gravitational wave is affecting the space between us and the pulsar by using the pulsar as the test mass directly. So we specifically use millisecond pulsars in our experiment. These are the most stable rotators that we know of. So the general idea is that as we have our neutron star, very dense, heavy, rapidly rotating, it is emitting a beam of radio emission from its magnetic pole. So the idea is as it sweeps across our line of sight, we, with our radio telescope, will see a bright pulse. So while the key to detecting gravitational waves with a detector like LIGO or LISA is, really in knowing our detector and experimenting with our laser interferometer, for a pulsar timing array, the secret really is timing. And while we've talked a lot about the gravitational wave sources, I do want to give you all a little bit of insight into how we actually do this pulsar timing. So step one generally is just observe our pulsar. So as our pulsar is rotating, it's emitting a nice casual chain of pulses that is coming very, very regularly. However, as well as we can model this, it's never going to be perfect. So if we subtract our actual times of arrival of these pulses from the actual model, we get what we call residuals. So as we actually go in and model these in more and more detail, we will actually start to see structure in these residuals. They're not just a perfect rotating neutron star isolated in space. There's actually quite a lot going on that will affect how well we can time them. Some things are, the pulsars are often in binaries. That binary motion will really drastically affect its residuals. It's moving across the sky and through the galaxy. The solar system itself is moving. There's also this little thing called the interstellar medium that gets in the way. It disperses all of our pulses and affects that radio light that we observe with our telescope. And then finally, gravitational waves, which is what we really want to dig through all of this data to look for. So if we can time our pulsars perfectly, we will get a nice, flat, Gaussian distributed white noise chain of residuals across all of our timing data. The general idea then is that as the gravitational wave passes, it squeezes and stretches space-time, and then that will affect each pulse time of arrival to arrive either a little bit earlier or a little bit later. So in this GIF, you can see a nice visual example of this. So as our gravitational wave passes, it both stretches space-time, and we can see our train of pulses stretch apart when it turns red. And then as the opposite end of the gravitational wave comes by, you can see it turn blue. The pulses are more compacted, so the residuals would form a nice, steady sinusoidal pattern. However, to actually be able to detect gravitational waves, we can't just time a single pulsar. We really need to look at these all across the sky, all throughout the galaxy, to actually make sure that what we're going to be seeing is gravitational waves. Without that, we would not be able to tell if what we were seeing were, some individual timing structure within the pulsar itself, or some broader effect like a gravitational wave that should affect the entire detector together. So when we do this, we compile tons and tons of data. So here is an example of Nanograv's 15-year data set and a representation of every observation that has been taken to compile that entire data set. So you can see that the longest time pulsars have been timed for a time span that equates to just over 15 years, so hence 15-year data set. But you can also see that over time, we've gradually added pulsars. So some of them have been timed for a very long time, others have been timed for less time. Those are the ones that have been added later. So while we both extend our baseline in every single data set, and we encompass and include all of the data that has been collected already, we are constantly adding pulsars, refining them to learn more and more about them, but also get more and more sky coverage so we can do a better job as we do our gravitational wave searches. If you look very carefully in this figure, you'll see there are a few gaps, things that correspond to things like telescope maintenance, certain telescopes unfortunately being lost from our array, but in general, every data point is always going to be included going forward. The other complication is that unlike our ground-based detectors where we know exactly when they're on, when they're observing, and they're observing very regularly, our telescopes are not able to observe at a perfectly even cadence. So we need to make sure that we can account for when all these observations are taken, the fact that they are irregularly spaced, they may be observed for different amounts of time, and make sure that we can do our analyses as accurately as possible. So this also is not just a North American effort, of course. We exist within this structure called the International Pulsar Timing Array, where we team up with pulsar timing arrays from around the world. It's based in North America, Europe, China, Australia, India, and South Africa to do better than any of us could alone. The general idea being is that the more observations you have of any individual pulsar, you'll be able to time it better and better. And it's truly a combined effort when we actually put all of this data together. Rather than just being able to just look at the data kind of separately, each pulsar is actually retimed and recombined when we make one of these joint data sets. So we interleave all of those observations, so we have more telescopes to consider, more backends, more noise sources, but we can learn more and more about those pulsar effects to study them better and better, and then hopefully have a more sensitive gravitational wave detector. So turning over to the gravitational wave side, we've heard a lot about supermassive black hole binary and spirals this week, but just as a reminder, so one example of a source that we might look for in a pulsar timing array is a continuous gravitational wave from a single supermassive black hole binary. In this movie here, I have placed a supermassive black hole binary at the center of the sky and shown the effect in residual space on the map, changing over time, as well as its effect on 3 example pulsars shown in the red, blue, and yellow curves on the bottom right. So you can see there's a steady sinusoidal change in the time of arrival of the pulse times of arrival, but each pulsar has a different amplitude response depending on where it is on the sky. And that is the that is the fact that we will use to actually go back and correlate where such a source would be coming from. That's why it's so important that we have multiple test pulsars all across the sky. However, again, as we've heard a lot this week, supermassive black hole binaries do not exist in a vacuum. We don't think there's just one out there in the universe. We actually think there are many. So while we like to look for continuous gravitational waves from individual supermassive black hole binaries, what we actually think within the pulsar timing array regime will be the most detectable source is going to be the gravitational wave background made up of all the supermassive black hole binaries in the universe emitting gravitational waves together. So here I've taken this movie and multiplied it by 200. So if we place 200 gravitational wave sources all across the sky and then have our test pulsars looking at the residual effect and their times of arrival, this is what we see. You can no longer trace back any of those individual sinusoids from any of those individual supermassive black hole binaries, but there's a very obvious gravitational wave influence on these residuals. And what it actually ends up being is a correlated red noise process. So this is made up of a few different parts, just to give you an intuitive sense. The first part is the red noise part. So as Katie lovelily described yesterday, so now I don't have to, when you take the distribution of binary inspirals and the rate at which they inspiral and combine them, what we see is that we will have more sources that are emitting at low frequencies, fewer sources that are emitting at high frequencies. When you combine that with the amplitudes of the gravitational waves they will emit, what we end up seeing is this red noise spectrum that has this negative spectral index. That if we were to take the Fourier transform of any of these time series, that would be the spectrum from the red noise that this is drawn. And what's really important to think about is that when we look at our pulsar data sets and we are able to analyze them each for red noise, we would see that they were drawn from a common spectrum. So that's the first piece of evidence that we need to look for. The second is this correlation effect, which can be kind of subtle to think about, but basically all it means is that if we were to look at these residual patterns between, for example, the red and the yellow pulsar, we would see that they're more or less independent. They don't really care about each other. However, the red and the blue pulsar are a little bit correlated. They're closer together on the sky. They care more about what is happening in gravitational wave space across the sky. The opposite is true for the blue and the yellow pulsar. They are actually anti-correlated. If we are able to use many, many pulsars and build up this correlation pattern, what we would see is a correlation pattern that would be distinct to gravitational waves, called a Hellings and Downs correlation pattern, rather than something that might be induced by a non-gravitational wave source. Another way to visualize this is as we look at pulsars all around the Earth, across the sky, an uncorrelated red noise pattern, we would not see any trend as we take the correlation coefficient between the red noise spectrum in a pulsar two pulsars that are close together versus two pulsars that are on the opposite sides of the sky. However, if there is a gravitational wave origin at play, we will see that we will slowly build up this Hellings and Downs correlation pattern as we look at different pulsar pairs across the sky. So in Nanograv's 15-year data set, when we started to do this, this is what we saw. So you can see that we are starting to see evidence of a Hellings and Downs correlated red noise process. So I'll move on right here. Many of you may have seen these results over the past year, but I do want to make sure for those of you who have not before, we give you a brief overview. So in our 15-year data set, we see both a red noise spectrum that is consistent with what we expect for gravitational waves, as well as Hellings and Downs correlations that we see at a significance of about 3 to 4 sigma. So we're starting to see evidence of this gravitational wave background, but there is quite a lot more that we can learn about it over the next few years. So the first thing that we wanted to do is check in with our international partners and say, okay, we're starting to see this. Who else is starting to see it? What can we all say about it together? And it turns out that everybody is seeing a very similar and consistent signal in all of our separate data sets. So you can see in this top left figure up here, we're comparing the red noise spectrum between the European pulsar timing array, nanograv, and the Parkes pulsar timing array down in Australia. We also then make a joint posterior analysis to see if all of these results get better when we will be able to combine the results in the future. And we do see that that is the case. You can see the 2D posterior here. The black contour is when we were jointly analyzing all of our data together. However, I do want to emphasize that this is not yet a fully combined data set. When we combine all of these data sets together into a truly combined data set, where we retime each of these pulsars to get better and better timing solutions, extend all of our baselines, and use all of the data that we can, we expect the significance increase to grow even more. So, many of you, I know, like me, are interested in what this actually says about the gravitational wave sources. So the first thing we do is we fit this gravitational wave spectrum with a pure power law. And at first, what we saw may indicate that our recovered spectral index might not look that consistent with the supermassive black hole binary origin. The spectral index of a supermassive black hole binary gravitational wave background is going to be a gamma of 13/3 or a alpha of -2/3. And we can see our 2D posterior between amplitude and gamma way over here, which means it's a very shallow background. However, when we did really extensive simulations of what realistic populations of supermassive black hole binaries look like, we actually see that there's really significant overlap. While the mean of this red contour will be at this -13/3 value, we actually see that there's quite a lot of spread, much of which is consistent with the spectral index that we measure in our data set. However, we can go a step further, and we can actually model all of the phenomena that we think will help our supermassive black hole binaries come together and merge. They don't exist in a vacuum. Again, we've heard a lot about this week. While the gravitational wave only background would follow this dotted black line up here, there are quite a lot of things that can help drive our supermassive black hole binaries to merge even faster than we may expect and give us a different background shape. So for example, there might be interactions with a circumbinary disk, there might be stellar scatterings, or there might be eccentricity in this population. So as we look at that, we see that when we model all of these phenomena, we actually get this blue contour, which spreads over an even broader range of parameter space, which means that more and more we see that what we have measured is absolutely consistent with supermassive black hole binaries. We also do measurements to expand beyond just this power law model, just to see how consistent our measured background parameters are with a truly phenomenological gravitational wave background model. So including all of the different spectral shapes beyond a pure power law. While we see that our best fit model does move slightly beyond the power law, we can see the measured posteriors in each frequency bin shown in the gray and green violins, and the overall background shape in this blue curve here, really both fit more or less equally well. So we really will need more data to say, do we prefer having this environmental impacts or just gravitational waves driving this background? However, what's important to remember is that we do not know for sure that this gravitational wave background is coming from supermassive black hole binaries. We think that that is the most likely candidate, but there's also plenty of models that are consistent with gravitational waves from cosmological effects. So things like cosmic inflation, scalar-induced gravitational waves, cosmic strings, all kinds of things. And more or less all of them are consistent with the data. So you can see our data down here in gray, those are those gray violins from before rescaled into a different unit, as well as all of these different models. All of them could be consistent. One last thing that we wanted to do before moving on from this data set is do searches for these individual supermassive black hole binaries and search for the continuous gravitational waves in our data set to see if any were there, even though we expect the dominant source to be the background, but we want to make sure we do our due diligence and look for any continuous waves that might be in there as well. So In the 15-year data set, we see no evidence of any continuous waves. While there are some structures, as we're looking at our evidence on the y-axis here across gravitational wave frequency, down here at this low frequency bump, once we account for the gravitational wave background, perfect, thank you. We do not see any excess of evidence. Up here at high frequencies, you can see there's this very bright green marker where there's this high increase in base factor that actually corresponds to a known pulsar binary orbital period, namely our most sensitive pulsar, J1713. So this is a known degeneracy in the model where we do not expect this to actually be a continuous wave. We expect this to be due to this pulsar binary. But more time will tell if anything does resolve. But what is nice to know is that we do see our limits on our continuous wave sensitivity increasing across the sky. So we can now see continuous waves or put limits on them out to distances of up to 150 megaparsecs in our most sensitive part of the sky. And what I think is really exciting is you can see all of these little black dots on this plot up here. All of these are electromagnetically derived supermassive black hole binary candidates. So what I think will be really exciting in coming years is we can treat these candidates as a little signpost to say, hello, I am here, look at me, look for me. So we can target some of these individual supermassive black hole binary candidates with our pulsar timing array detector and hopefully be able to either confirm or deny their supermassive black hole binary origin. So many of you might ask, what is next? We've reached this point. Where do we go from here? We just had our annual International Pulsar Timing Array meeting 2 weeks ago in Sexton, Italy, where most of the goal of the week, in fact, was to answer that question. So it really was perfect timing for me to go there and then come here and give you all the inside scoop of what is coming up next. While a lot of that work is still underway, so I can't show too much of it, I can show you a few of my favorite takeaways. So first question, when more data? So International Pulsar Timing Array Data Release 3 is currently in progress. As I've mentioned before, this is a really big undertaking to actually do all this data combination. Our best guess for when this will be released is hopefully sometime next year. So definitely keep an eye out, but know that we are working as fast as we can, and we want to be respectful of our timing colleagues who are doing all this data combination, while we here on the detection side are doing our best to be prepared with all of the analysis techniques that we will need to analyze this large, huge, incredible data set. One of the next exciting things that I will be really thrilled to see is that new telescopes are beginning to contribute data as well. In nanograv, we're particularly excited that CHIME, the Canadian Hydrogen Intensity Mapping Experiment, is going to be starting to contribute data in our next data set, the 20-year-long data set. This telescope will actually give us daily cadence on many of our best pulsars, which will be really transformative for our gravitational wave searches, but it's also transformative in the way that we will need to treat the data. So again, while we are excited for these data sets coming, hopefully in the next year or two, it is taking a significant amount of effort to actually do this combination and account for the huge increase in data volume that we're going to see over the next few years. Related, along the way, as all of this is happening, we're constantly developing new gravitational wave analysis software. So because of this huge increase in data volume, as well as the increased number of analyses that we need to do to reliably analyze all of our significance levels, as we're starting to find evidence for this background, they need to run faster and faster. So people have been doing really excellent work in speeding them up. Finally, we're also investigating what needs we have for advanced pipelines. So as we are starting to see evidence for this gravitational wave background, we need to not forget about our other searches and how that background might impact them. Doing joint searches, for example, between continuous waves and a gravitational wave background, you all know is very complex. So we are working on getting that into a working order so we can make sure we can be as accurate as possible. What this all means is that we're having some really exciting opportunities for the future. Our first focus is going to be improving our gravitational wave spectral constraints, and that will be able to give us better limits on these supermassive black hole binary populations and what we can infer about them. And ideally, our constraints will only increase with the new data sets that are coming in the coming year. I see I'm just about out of time, so I'll rush through. We also will be learning about new signals and statistics that we will hopefully be able to look for in our future data sets. This is where many of my colleagues are getting really excited. And finally, we also want to make sure we are synchronizing with other observatories, so we are preparing ourselves for a multi-messenger era where we can look for these gravitational waves, both in our pulsar timing data as well as electromagnetically. So for many years, many of you may have had the impression that over time, we're approaching the end of a very long road where we've been doing this pulsar timing effort for decades, and now we're reaching this era where we are observing a gravitational wave background. But from my perspective, the road really looks something more like this, where we've been working for a long time, but the road ahead is really exciting between all the things we can learn about the background, individual supermassive black hole binaries, studies of new physics, and more. Especially synchronizing with LISA, where we can learn more and more about the population of gravitational wave sources across the gravitational wave spectrum. Thank you.
Thank you very much. Questions? Yes, over there.
Hi, thanks. This is great, though I don't know that much about pulsar timing. With chime and this daily cadence, does that mean you can push up your high frequency sensitivity some amount, get to lower mass sources maybe?
So while I would love that, I think a lot of the reality of those high frequency continuous wave sources is that the limit is, while Fourier analysis would tell us that the absolute limit is the separation in our observations, in reality, our white noise gets really, really significant up there. So things like, as I showed, this pulsar binary orbit, interactions with all of our different receivers and white noise, I think there would be a lot of work needed to actually push that up. But it's something I would love to investigate because those high frequencies could be really rich with information.
Thank you. There's a question, and then afterwards over there.
Yeah, great talk. And I had a question about the map where you were highlighting some of the suspected EM identified.
Oh yeah.
Possible binaries. And if I remember correctly, I think sort of the sensitivity range for the PTA timing is going out to maybe like 160 megaparsecs. And like OJ287 and PG1302, which are two of the best characterized EM plausible counterparts, is like a little more than a gigaparsec.
Yeah.
So how much more integration time do we need to potentially see that? And given that they have been intensively modeled and we have suspicions about the parameters, does that give us can we do better basically than a blind search because we have like a bet on the frequency and masses, say?
This is an excellent question because this is actually this is where my focus lies actually in multi-messenger astronomy. So I did simplify a little bit extra here. This luminosity distance limit is mass dependent. So for a 10 to the 9 solar mass binary, this is the scale we are about sensitive to. For a 10 to the 10 solar mass binary, it goes up to order almost a gigaparsec. So all depends on what we actually think the chirp mass of these sources is going to be. But overall, I always do stress to people that we need to be thinking about local universe sources. So while we can push things up to luminosity distances of nearly a gigaparsec, we are going to get much better limits and things in the local universe. The second part of your question was if we can learn anything more with really good models. So we have done targeted searches for some of these supermassive black hole binary candidates, and there's more being done with the 15-year data set. Nikita Agarwal, London Wilson, and Bjorn Larsen are all working on this within Nanograv. There's also some work being done within the IPTA. And what we see is it's actually very frequency dependent, where the limits actually get helped by this targeting scheme. So it does help our search not to have to search over the sky. That's actually a really complex part of our parameter space. But the most important thing is if you can narrow in that frequency, even into an order of magnitude, we can do better than the all-sky search, but not dramatically better.
Thank you. There is a question up there. Last question.
It was a neat talk. Two questions about network. One, will Meerkat be contributing to the results that are going forward? I think a really neat contribution from that could be good. And the other is whether or not the international part is taking hold. Will future publications be IPTA publications, or are you going to continue with a kind of multiple output approach?
It's a hefty question. So to my knowledge, Meerkat PTA is starting to produce data. I'm not sure about the timeline to which they will be able to contribute fully to the IPTA. There are, political concerns and other constraints where I know some of our international colleagues really want to be contributing data, and some of them cannot. Meerkat, I'm not 100% sure what the timeline is, but I could check and get back to you at coffee. Yeah, Rucker, do you know? It'll be in? Good, thank you. I couldn't find the slide before the talk. Thank you. So it will be in. Second part of the question was, will future publications be all IPTA? So I do think that we will continue analyzing data in the individual PTAs just because of the really complex needs to combine them immediately directly into IPTA. It's not ever going to be something that is going to be a rolling continuous contribution. It is going to have to be staged. But I think we do see a future where the IPTA data sets will become more and more regular and the analyses will be done more and more streamlined.
Okay, thank you. Then we